All right, page number 3, we're going to start talking about periodic trends. So periodic trends are referring to patterns that occur on the periodic table, and there are 5 that we're going to look at. We're going to start with the first 2 on this page. So the first thing we're going to look at is called atomic radius. If you remember the word radius from math class, radius means for a circle measured from the center to the edge of the circle. For chemistry, the way that we do this, we can't really measure the edge of an atom very well. So what scientists will do is take the 2 atoms when they're bonded to each other, measure from the middle to the middle, and then divide it by 2 to just get the radius. So this is the distance between nuclei of identical atoms bonded together, and then they take it and they divide it in 2. So it's half the distance between nuclei of identical atoms. Again, really, it's just the idea of if I have an atom from the center to the edge is the radius. For the periodic trend that we see, as we move from left to right across the periodic table, if you look at this picture, you'll notice that there's a pattern. On the left side, it's bigger, and then as I move to the right, the atoms become smaller and smaller. So our period trend, the radius decreases across a period. This one's a little bit strange. It's pretty common to think that as I move from left to right, the masses are getting bigger, there's more protons, there's more neutrons, there's more electrons. We typically would think that the atom should be getting bigger, but that's not the case. So the reason why the atoms get smaller as we move across is as we're moving across, we're increasing the atomic number, which is the number of protons, and we're going to end up having a greater positive charge in the nucleus, but we still have the same number of energy levels of electrons. So we still have the same number of rings of electrons around the nucleus. What this is going to do when there's a greater positive charge in the center, electrons are going to be held more tightly or closer. So electrons are held more tightly by the nucleus, so the nucleus holds them closer, which results in a smaller atom. Because this is a little tricky to understand, I want to just do kind of a quick analogy. Okay, I want you to picture that we have each proton is going to be $100. Okay, so this is going to be my protons. I'm going to put those in the center. If we have an atom like lithium, lithium has 2 rows of electrons. It has 2 electrons in the first row. I'm going to draw these as people. And then it has 1 electron in this second row. Okay. So if this is lithium right now, if I wanted to turn this into, let me draw $3 signs because it has 3 protons. If I wanted to turn this into beryllium, beryllium has 1 extra proton in the nucleus. So beryllium's going to have extra $ signs in the middle. And what that's going to do is make these people want to be closer to the money. So those people are going to try to scoot in even closer than they were before. And in this second row or the second ring, this person's going to scoot in closer. And this new person that we've added, the 4th person, is also going to scoot in closer. So the fact that this person's over on the right side of my picture doesn't affect the person on the left's ability to get closer. They are in a separate ring though. So this is kind of like saying there's a row of chairs and there's another row of chairs behind. You can't get closer than the people in the first row if you're in the second row, because if you're in the second row, you're by definition farther away than the first row people are. But that's why our atoms get smaller. When we start to put more money in the pot, more protons in the nucleus, that atom is going to compress, and shrink in order for all those electrons to get closer to the center where they're attracted. All right, our group trend. So if we look in a group on the periodic table, so if we pick group 1 and go down the group, you'll notice hydrogen's small, lithium's bigger, and then they get bigger and bigger until we get to the bottom here for cesium. So for a group trend, the radius is going to increase as we go down a group. And this connects back to the Bohr model. When we draw hydrogen, hydrogen has 1 ring of electrons. So hydrogen would have 1 ring. If we go to lithium, lithium's going to have 2 rings of electrons. Sodium would have 3 rings of electrons. And as I add more and more and more rings as I go down a row, my element's going to get bigger and bigger. Okay, so As we go down, we have more energy levels, our N value, which are filled, and these are farther away from the nucleus. As I add each ring, it gets farther. All right, a couple of practice questions. So we want to avoid using the periodic table that has pictures to answer these. So if we look at just a regular periodic table and we compare lithium or potassium, these two elements are in the same group, and our group trend says that radius increases going down a group. So if I wanted to know which one of these is larger, that's our question. So the one that's farther down would be larger. So that would be potassium. If we wanted to look at the next set, calcium or nickel, calcium is here, nickel is here. Our trend for going from left to right across a period, the radius decreases across a period. So if I'm looking for which one of these is bigger, it gets smaller as I go this direction, so the element that would be bigger would be calcium. For our last one, we have gallium and boron. So that's these two. And when we're looking at these, our group trend, elements get bigger going down the periodic table. So if I wanted to know which element was bigger, it would be gallium at the bottom. I'm just going to add a note on here. If we wanted to know which element was going to be the absolute biggest in terms of the period, radius gets smaller going left to right, so our biggest elements are at the left. And then for the group, the radius increases down a group. So I'd want my element to be on the left, but also towards the bottom. In the picture over here, that's cesium, but that's not the case on the actual periodic table. The very, very bottom left element on the periodic table is francium. So this little picture I put in the notes doesn't have the whole periodic table in it. So the largest element is francium, and our smallest would be in the opposite corner, right? Bottom left is the biggest, so top right is going to be our smallest, so we throw helium up here as our smallest element. All right, so from there, we're going to go on to what's called ionic radius. So ionic radius is still the radius, how big the element is, but of the ion that it makes, of the element's most common ion. Remember that ion means charged particle. So instead of looking at just potassium, when potassium makes an ion, it makes a charge of +1. So how would the size of regular potassium compare to potassium with a charge of +1? Two vocab words that we see on here, which are cation and anion. They're both ions, which means charged, so that's what that part means. Cation means positively charged. Positively charged. There's an E in there, huh? Positively charged. And negatively charged is anion. So if I say something's an anion, I'm telling you it has a negative charge. If I say something is a cation, that means it has a positive charge. So for our trend, we're going to skip down to the pictures down here. So if we have something that's a positive charge, so what's going to happen to something that's a positive charge, the way that an element becomes positively charged, is it has to lose electrons. Electrons have a negative charge. If you lose negatives, you become positive. If you're negatively charged, then that means that you've gained electrons. Electrons are negatively charged, so the only way to become negatively charged is to get extra electrons. So if we picture these changes occurring, so if we wanted to know, well, in which case is the element getting bigger? Is it getting bigger when it loses electrons or gains electrons? Electrons are on the outside of the atom, so if I want my atom to get bigger, I want there to be more electrons. If my atom gains electrons to become an anion, then they're going to have a larger radius than their neutral atom. So if you look at something like sulfur, that's how big sulfur is. If sulfur gains 2 electrons, now it has extra electrons in the cloud, it's now larger. On the other hand, if we have an element like lithium and it's going to lose electrons, those electrons are all spread out. When it loses some of them, now we're losing a whole ring in our Bohr model. Lithium, when it's neutral, has 2 rings of electrons. It has 2 electrons in the first ring and 1 in the second ring. But when lithium becomes a charge of +1, it loses this electron, and now it only has 1 ring of electrons. So it gets smaller because it lost a whole ring of electrons just by losing that single electron overall. So cations, when an element becomes positively charged, they're going to be smaller than their neutral atom. If we compare across a period and across a group, so if we look, across here, for example, and we compare lithium +1 to beryllium +2 as I move across the period, so the cation here is getting smaller. So that's the same trend that we saw before. Get smaller or decrease. Cations decrease in size. If we look over here at what happens to our anions in the same row, we see that we have something that's 1.7, goes to 1.4, goes to 1.3. So we see the same trend moving across. If we're looking at all ions in a row, we see the cations decrease, we see the anions decrease across a period. Just as a reminder, notice that we see the halogens here, but there's no group 18 shown. Noble gases do not make ions. So we're never going to talk about the ionic radius of a noble gas because they don't form ions at all. If we look at the group trend, what happens to the size of an ion as it moves down the group? This is the exact same trend we saw before as well. The elements are going to get larger, so tends to increase or get larger as we move down a group. And this again goes back to the Bohr model. Outer electrons are farther from the nucleus because there's more energy levels. So our elements get bigger and bigger going down a group. So this part is really just a repeat of what we already said. All right, let's look at a little bit of practice. So for our first one, we're looking for which one's smaller. So potassium or potassium with the charge of +1. Remember that when something is positively charged, this is backwards from what you would normally think. You usually think positive means gain, but in chemistry, positive means lose electrons. So if I want to know which one's smaller, is it the one that was neutral or the one that lost electrons, which sounds smaller? It's going to be the one that lost electrons. It's the one that's tinier. If we look at iodine or iodine with a charge of -1, minus means gain electrons. If I want to know which one of these two is going to be bigger, regular iodine or iodine that's gained extra electrons, which one sounds smaller? That would be just regular old iodine. For our next one, we have aluminum +3 and phosphorus -3. So this one's a little bit trickier. So if we look at that, aluminum, when it becomes a +3, that means it's losing 3 electrons. So it loses 1, 2, 3 electrons. So it's going to be kind of similar to the size of neon. Phosphorus, when it's a -3, that means it gains 3 electrons. So it's going to go 1, 2, 3. So this is going to be kind of similar to the size of argon. Not exactly, because it's a different element. But if I wanted to know which one of these two is going to be smaller, the element that's kind of like neon, that means that it has 2 rings of electrons. Or the one that's kind of like argon, that's going to have 3 rings of electrons. And we wanted to know which one of these two was smaller. That's going to be the one with fewer rings. So aluminum with the charge of +3 is smaller than phosphorus because it lost electrons to get smaller. Phosphorus gained electrons to get bigger. Those are the first 2 of our periodic trends, looking at the size of atoms and the size of ions. And on page 4, we will be looking at the last 3 of the periodic trends.